Hi everyone, I'm going to implement convolutional neural network in Microsoft Excel. So this is what you can expect as an output. Over here we are giving an input image which is nothing but bunch of zeros and ones, where 1 is the white pixel and 0 is the darker pixel. So after doing the convolutions and after connecting to a fully connected network, the final output that we are going to get is this. So it is predicting that the given number is a 0. And that is correct. The given input number is a 0. I can change the input number, so let me paste in a different number. So this time the input number is 2. So with the same weights and biases, after performing the convolutions and the fully connected network, the final output prediction is that the input number is a 2. And we can try with a different number as well. So let me try with the number 7. So with the input as 7, after performing all the convolutions, the final prediction is that the given number is 7. So this particular neural network is already trained and it is having a 97% accuracy. And I have already imported all the respective weights into the Excel. So what we are going to do is we are going to use the existing weights which I have extracted from the network, and then we are going to manually do the forward process. We're going to manually compute how we are going to start from this image and finally how we are going to end up with this prediction. The entire process we are going to manually calculate it. So let's get started with the architecture of the model. The architecture of the model contains three different layers. We have convolution layer 1, convolution layer 2, and then finally a fully connected neural network which is having 10 neurons as the output. Here each neuron represents the probability of the input being that particular number. So for example, if the input number is 3, then the neuron 3 will have the highest value compared to the other neurons. And if the input number is 9, then the probability or the value of the 9 will be the highest compared to the other neurons. Let's dive deep into each convolution layer and understand how that works. So the convolution layer 1, it reads an input of matrix 1 by 28 by 28. Here the 1 represents the number of channels. Because this is a black and white image, we just have one channel. If this were to be a color image, we will have three different channels, red, green, and blue. And the 28 by 28 represents the image resolution. So the first step that we are doing is applying a convolution with two kernels, each of size 5 by 5. Because we are using two kernels, we will have two different matrices as the output. And the size of the matrix is going to be 24 by 24. So we can say that the output of the first convolution is two channels, each channel of size 24 by 24. And after we get this, we are going to apply a ReLU activation. So the ReLU activation function is essentially going to remove all the negative numbers and leave the positive numbers. If you have any negative number in the output, that is going to be replaced with a 0. That is how the ReLU activation function is going to work. The second step in the convolution layer 1 is applying a max pooling with a kernel size 2 by 2. So this is essentially going to reduce the dimensions of the input. So here the dimensions of each channel is 24 by 24, that is half. So you have 12 by 12. The number of channels does not change, but the resolution or the size of each matrix will be halved. So you have 12 by 12. And then convolution layer 2. So convolution layer 2 is going to read the input of convolution layer 1, which is two channels, each of size 12 by 12. And then we are going to apply four kernels, each of size 3 by 3. So after this operation, because we have four kernels, the output is going to be four different channels, each of size 10 by 10. And then we are applying an activation function called as a sigmoid activation function. So sigmoid activation function is going to squeeze the numbers between 0 to 1. So whatever the numbers that are there in the matrix, that are going to be squeezed between 0 to 1. And then we are taking these four outputs, applying max pooling to that. So similar to what we have done previously, after applying the max pooling, the size of the channel is going to be 4, but the resolution of each channel is halved by 2. So we are going from 10 by 10 to 5 by 5. And then finally, we are going to flatten this data. Flattening the data is nothing but each matrix is having 5 by 5, so that is 25 data points, and we have four different matrices, so that totals to 100 different data points, and we are representing all these 100 different data points as an array of size 1 by 100. And then this data is fed into a fully connected neural network. In the fully connected neural network, each neuron is connected to every single input. So 0 is connected with 1, 0 is connected with the second input, 0 is connected with the 100th input. And similarly, the first neuron is connected to the first input, second input, and so on to the 100th input. So in this way, every single neuron is connected to every single input. We are going to perform a weighted sum operation, add a bias to it, and then finally apply a softmax activation. Alright, let's manually apply the convolution layers and fully connected layers in the Excel for this particular neural network. So let's start with the input image. Here the input image is a bunch of numbers, each number representing the luminescent of a pixel. So if a number is 0, that is a darker pixel, and if a number is closer to 1, that is much brighter pixel. So one thing to note is that when you are pasting this data, so for example, this is the data. Here 0 represents a black color and 1 represents a white color. So it does not look good by default. What you can do is you can reduce the width of the columns. So you can select all the columns and then change the width of the column to something like 3 or whichever is more suitable. So this is going to convert each cell into a square. And then after that, you can apply some color formatting to it. So you can select the entire image, go to home. You have something called as a conditional formatting. You have a color scale, and then you can apply various color scales. I'm going to stick with a yellow and green, where the brighter pixels are highlighted in yellow and darker pixels are highlighted in green. You can also look at the original image by changing this to black and white. So for example, I can say that the lowest value, or the number 0, represents a black color, and the highest value, or I'll switch that to a number 1, which is the highest value, that represents a white color. By doing so, I can look at this number in its original format, which is a black and white image. But I'm going to stick to this green and yellow formatting as it is much pleasant to look at. To perform a convolution, what we have to do is we have to take a look at the size of our kernel. So in this case, it is 5 by 5. So let's take a window of size 5 by 5. So let's go to insert, let's pick up a shape. I'll pick up a triangle, and then we need to have a 5 by 5 triangle. So that is 5 and 5. And then I'll make it transparent or no fill. So we have this particular window. We can move this window across. So let's position this window at the first top left corner. So we have 5 values within this window. So what we have to do is we have to multiply these 5 values with the values that we have in the kernel. So let's do that manually first. I'll copy the values of the kernel, paste it over here, and then I'll copy the values that we have within this box and then paste that here. The next step that we need to do is, let me zoom in a bit. The next thing that we need to do is perform a multiplication. So this is equals to this multiplied by the value that we have in the kernel. And then let's repeat it 5 times in this way and then 5 times in this way. So if I click here, so this is, we are picking up this particular value and then multiplying it with this particular value. So that is the multiplication part of the convolution. This is an extra one, let me delete it. And then the next thing that we are going to do is we are going to perform a sum operation. We are going to sum up all these values. So this is the result after multiplying, and then we are performing a sum. So after performing a sum, we got the number as 0 because pretty much all the inputs are 0. And to this, we are going to add a bias. So we are going to pick up the sum plus add the bias value. In this case, the bias of the first convolution is, or the first kernel is 0.6. Let's add that. So adding a bias will result in a value of 0.6. Or to be more specific, it is going to be 0.58. So we are going to copy this value, and then that is the new value. That is the output of the first pixel or the first grid value for the convolution. So let me paste in our value. Now let's slide this window. So this is the first part that is done. Let's slide the window slightly to the right. Now we are going to pick up these 5 values, copy them, and repeat this step again. Paste it over here. And this time we don't have to do it again because this is already calculated. The result is still the same. It is 0.6. So you can paste the value of 0.6 in the next column. So this is supposed to be here, sorry. And then in that way, we are going to slide this across this entire image. After that is done, we are going to slide it down. So we are going to skip the first row. We are going to start here. We are going to copy these values and then do the convolution. So this is a manual process. This is tedious, but lucky for us, Excel already provides us with an inbuilt function, which is called as sum product. So we can use that. We can say sum product of the first array. So the first array is the kernel that we are using, comma. The second array is the values. So 5 by 5. So this is the second array. And then let's do that. So as you can see, it has performed the convolution, and we have to finally add a bias to it. So plus whatever the bias we have, I'm adding a bias. Awesome. So now we have the value 0.6, that is correct. So before we drag this to the entire matrix, we have to make a small change. So if I directly drag it, you can see that the box that we have over here on the kernel, this is also moving. We do not want that. So this has to remain constant, whereas this particular box, this highlighted in red, should move. So what we can do is we can use something called as a constant reference. So I can click over here, and then I can say that the kernel values are constant by adding a dollar. So this is going to make the kernel values a constant reference, and the same goes for the values for the bias. We do not want that Excel to automatically move the bounding box, so we're going to make them a constant reference. After doing that, let me zoom out a bit and then populate this entire matrix. And then let me drag this down till here. So now if you look at it, if I click on the corner right over here, we are doing a sum product on this particular kernel multiplied by values that are over here at the corner of this image, and then adding a bias. And then if I take a value that is just above, one row from the bottom and then one row from the right, if I see this, we are still picking up the values from the kernel and the bias as well, but whereas here we have also shifted this bounding box to one row above and one row from the right. So in this way we can perform a convolution, and we haven't applied a ReLU activation yet. So as I have mentioned, what a ReLU is going to do is, if you see a negative value, that is going to be replaced by a 0, and any positive value like 2.9, 5.6, etc., they are going to remain as it is. So to apply a ReLU, it is quite straightforward. So we can say that if this particular value, let me copy this. So if this particular value is greater than 0, then use the exact same value. If not, which means that if the value is less than 0, replace the value with 0. So that is the change that I have done. And now I can populate this entire thing and then drag it down. So now you can see that all the places where we previously had a negative value, they are replaced with a 0. All the positive values are remaining as it is. There is no change to that. And we can do the exact same thing using the second filter. So as you can see, we have a second kernel. So we can generate another image by multiplying these 5 values with the first 5 values and then doing a sum and adding the bias. So let me do that really quickly. So this is applying a convolution with an activation function of ReLU. Alright, the next thing that we are going to do is apply a max pooling. So this is our input, and we have to essentially find out the maximum value. So let me zoom in a bit. This is going to look something like this. This is equals to max of these 4 values. Let me pick these 4 values here, close the brackets, done. Alright, and then for the second part, I'm going to say max of this time we are going to skip two values and we are going to pick up the next two values, and that is that. And for as we go to the next row, that is going to be max of. So we are going to skip the first two values. We'll pick up the next two values and find a maximum. So in this way, we are applying a max pooling. But of course, applying it manually is tedious, and unfortunately, you cannot drag and drop. So if you were to drag this, it will be incorrect. Excel is not going to skip two values. So the alternative that we can use is max of. We're going to use an offset. So I'll use an offset, and these are going to be a constant reference. So this is going to be offset by rows. So the first value I'm not going to offset by anything, so that is 0, comma, height. And then again I'm going to make some constants. So over here I want the number to be a constant one. Sorry, the number has to increase but not the column. So this is going to be $, and then for the BN part, so the number 4 is going to be a constant. And of course I need to close the brackets. Awesome. So if you are a bit confused by what I have done, that is fine. You can still entirely manually populate this array as what I have shown previously. You can select a value. You can do that is equals to max of, and then select the two values, apply the maximum, and then that is equals to max of. Skip two values, go to the next one. You can always do it manually. So this is a small trick that I have used in Excel so that I can populate it much faster. Okay, so if you take a look at this now, the expected output is that it should look pretty much similar to the bigger image, but it should just look smaller. So basically we are reducing the resolution of the image, so this and this should look similar but a bit smaller. And let's do the same over here. So this is how we can apply a max pooling. With this, we have actually completed the first convolution layer. We have taken an input image, we have applied a kernel to it, and we got a convolution of that. By applying this kernel, we have a convoluted image. We have done the same. We have taken the second kernel, applied the convolution with the original image, and then we got the second image. After getting this image, we have applied a ReLU function, which is nothing but if the number is less than 0, make it 0. If it is greater than 0, leave it as it is. And then we have applied max pooling, wherein we are picking up 4 cells, and we are picking up a maximum value from these 4 cells. And then we are picking up the next 4, picking up a maximum value. In that way, we are picking a maximum value. After this entire row is done, we are going to the next row. We are picking up the next 4 cells. In this way, we are picking up a maximum value and then populating it over here. So this is the first convolution layer. So for the second convolution layer, we have two inputs. So this is the first input that we're getting from the previous convolution layer, and this is the second input. And if you look at the architecture, we are using 4 different kernels when it comes to the second convolution layer. So these are the 4 kernels that are displayed here. Now, if you take a look at it, we have 4 kernels, but we have them in the sets of 2. That is because we have 2 input channels. This is the first input channel, and this is the second input channel. So if we were to have, let's say, 6 input channels, then we'll have 4 sets, each set having 6 kernels. So in this case, let's say that if you were to have 6 input channels, then you'll have 1, 2, 3, 4, and 5, and 6. So in this way, you would have multiple kernels for a given set. So in our example, we just have 2 channels as an input. So we have 2 kernels per a given set. And in total, we have 4 different sets. The second item is that we will only have 1 bias for a given kernel. So in this case, we have 4 sets of kernels, each set having 2 different kernels. But as you can see, there is only 1 bias. Even if we take an example wherein you have 6 channels as an input, in that case you have 4 sets, each set containing 6 different kernels, you will still have only 1 bias for a given set. So that is how the bias works. Now, how do we compute it? So in the previous case, it was quite simple. You had 1 input, you have 2 kernels. So you're making a convolution between kernel 1 and the input image to get the first output. You're doing the convolution between the second kernel and the first image to get the convolution. So in this case, it is similar. We take the first kernel and then we apply convolution with this image. We get a result over here. And then what we are going to do is we are going to take the second kernel from the set, and then we are going to apply convolution for the second image, and then we are going to sum up the previous value and the new value. After that, we are going to add a bias. So that is how we are going to do it. So let me show you an example. In this case, the first part is going to be the same. We are going to use the sum product function, which is going to take two inputs, the first array, which is our kernel, and then the input. So within the input, we are only selecting 3 by 3 because our kernel size is 3 by 3. We have selected a 3 by 3 matrix. And then we are going to make the kernel as a constant reference by adding a dollar sign. All right. So that is the output of the first kernel, and then we can simply populate this. So this is done. So if I click somewhere, we'll see that we are taking this value of the kernel, we are multiplying with these values, and then we are making a sum of it. So the next step is we have to add the kernels. We have to make a convolution with this kernel, the second kernel, and the second image, and then add it to this particular image. So this is the existing sum product. For this, we are going to add another sum product, wherein we are taking the values of this kernel, and then we are convoluting that with the second output. And then to this, we are going to add the bias. So we have a bias over here, we're going to add this. And as usual, we are going to make the values of the kernel constant reference. And the same goes for the bias. All right. So, and let me just populate that. Okay, looks like I did not select the second item correctly. Let me do that again. Done. And then I can populate this entire thing. Alright, so to give you a recap, what we are doing is, we are doing the sum product between the first kernel and the first image, and then we are taking the second kernel and we are doing the sum product with the second image, and then finally we are adding up both the numbers. So this is the result of the first one, this is the result of the second, and then finally we are adding these two items, and finally we are adding a bias. So this is how we are going to generate a convolution when you have multiple channels as an input. Now, on top of this, if you look at this, we are using an activation function called as sigmoid. So the way the sigmoid function works is, it is based on the following equation. We are going to do 1 divided by 1 plus exponent of negative x. So over here, the negative x is the value that you have here. So in this case, the negative x would be minus 7.9. So the negative and the negative will be cancelled, and then you'll have positive 7.9. This is going to be positive 20, and if you have any positive values, those are going to be converted to negative values. So the positive 3.63 will be converted to a negative 3.63. So that is how this function works. So let's add that sigmoid equation in this. So this is our value. So what we want to do is, we want to do 1 divided by 1 plus the exponent of, and we have to multiply this entire statement by 1 so that we are getting a negative, or we are multiplying this value by a negative value, and then just close the brackets. So this is going to be negative 1 multiplied by this value. Awesome. So now let's populate the entire matrix. So once that is done, we are going to end up with an image looking something like this. So let's repeat the same process for the other 4 kernels. Alright, so I have applied the sigmoid activation function and I have performed the convolution for the rest of the items. So now we have 4 outputs. So we have output 1, output 2, output 3, and output 4. So these are the four outputs that we are getting after performing the convolution with four different kernels. And each kernel is a set of two different kernels because we have two channels as an input. So this is how we apply a convolution when you have multiple items as an input. And the next step is applying a max pooling. So similar to what we have done over here, max pooling is nothing but maximum value of these four items. And then you repeat the same, that is equals to maximum of the next four, and then that is equals to the maximum of the next four, and so on. With this, we have completed the second convolution layer as well. Now let's take a quick look at how the data is displayed. So let's go back to the first convolution layer. So initially we have a 5, and after performing the first convolution, we can observe that the initial convolution, or after making the convolution with the initial kernel, it is sort of highlighting all the vertical lines, the lines that go from top to bottom. So you can see that this particular line is much more brighter compared to the lines that are going from left to right. And then if I take a look at the second output, over here the lines that are horizontal are more brighter compared to the lines that are vertical. So with this we can understand that in the initial convolution, it is sort of trying to get the information about the lines that are going vertically in the first output or in the first channel, and in the second channel we are sort of getting the information about the lines that are going horizontally from left to right. So that is what we can sort of understand by taking a look at it. Now zooming out and looking at it, we can see that this is sort of an inverse of this image. So over here, the number 5 is highlighted in green. It's sort of highlighted. It is not exactly 5, but the shape approximately looks like 5. So we can sort of understand that this is making an inverse of this image where the number 5 is highlighted as zeros and the blank space is highlighted as ones. It is like an approximate version of it, and the last kernel is also looking something similar to that, and the rest of the kernels might be something where it is zooming in a bit at a specific area. After that we are applying a max pooling. So this is the final output that we are getting out of our second convolution layer. Alright, so we have completed the convolution layers of the neural network. We have completed both the convolutions and we are finally having this as the output. We have four different matrices, each of size 5 by 5. So before we move on to the fully connected network, we have to flatten this output. So which means that currently, if I go back to the architecture as I have mentioned here, so we are having data in this format. We have 5 by 5 matrices and we have four of them. So what we have to do is we have to convert that into a single large array which is having 100 items in it. So in order to do that, what we can do is we can directly is equals to this value and then just drag it along up to 5 digits, and then that is equals to this value and then drag it along up to the next 5 digits. So in that way you can sort of repeat this item, which I have already done it. Alright, so when it comes to a fully connected network, we are having 10 different nodes here. So we have 10 neurons and each neuron is connected to 100 inputs. So the neuron 0, it is having 100 weights. Neuron 1, this is also having 100 weights, and so on. Each neuron is having 100 weights, and also each neuron is having a bias. So normally to compute a fully connected network, what we'll be doing is that is equals to the neuron 1 weight multiplied by the input plus the second weight multiplied by the second input plus the third weight multiplied by the third input, and so on. So we do a computation in this way, and then finally we add the bias of this particular neuron. So this is how we'll be doing it. But that being said, it is a very tedious task, as you can imagine. You need to do it 100 times. As actually you need to do it 1,000 times because you have 10 neurons. So for each neuron you need to do it 100 times. So the much faster way to do it is using a matrix multiplication. So by multiplying this matrix by this matrix, we are going to get the same results. And Excel already provides us that function. We have mat multiply, wherein we can provide the first array, so which is our inputs, comma, and then we can give in the second array, which is the weights. All right. So as you can see, once I have done that, this data is automatically populated. So this is the weighted sum of the first neuron, this is the weighted sum of the second neuron, and so on. Now that we got w dot x, which is nothing but weights multiplied by the inputs, the next thing we need to do is add the bias. So this is straightforward. We take the result over here, which is wx, plus we are adding the bias, which I have over here. And then I can do the same for the other items as well. All right. So with this, we have the output of the fully connected neural network. And then finally, we have to apply a softmax to it. So the way the softmax algorithm works, or the softmax equation, is that we take the exponent value. So we take the exponent value of an x, and then that is divided by sum of all the other exponents. So exponent of x1 plus exponent of x2 and so on up to exponent of x3. So this is how we do it. So exponent of a particular x divided by exponent, let me change that to exponent of x1. So this is the equation. Let's actually implement it so that it is easier to understand. So this is equals to exponent of -14. And then we just populate it all the way across. That's it. And then finally we make a sum of it. So we just add everything that is equals to sum of all these items. All right. And then finally to get the output, what we have to do is that is equals to an exponent value. So in this case that divided by sum. And then we populate this across the board. Of course, over here the sum has to be a constant reference. And then we populate it across. Oops, we populate it all the way. All right. So now you can immediately see that the output neuron 5 has the highest value, indicating that the given image is a number 5. So let's quickly verify that. Well, this is 5. So we are getting the output as number 5. And we can do a quick check. Let me switch over to a different number. I have a data set over here wherein I have stored a bunch of numbers. So let's try with a different number, maybe a 9. Alright, so if I change it to 9, let's see the output. As you can see in the output, neuron 9 or the last neuron is having the highest value, indicating that the input is 9. So let's try with some other number. Maybe let's try with 6. So if I change the input to 6, we can see that the output is also a 6. It is predicting that the given input is a 6. Oh, so this is actually a 3, and it is predicting that the input or the output is actually a 3. So as you can see, it is doing a good job at predicting what is the output. So this particular model is actually having a 97% accuracy on the training data. So this is how the convolutional neural network works. We are taking an image, we are applying convolutions, and we are getting 2 channels, and after that we are applying more convolutions, and then finally we are performing a fully connected layer wherein we are doing weights multiplied by inputs and adding a bias. After that, finally applying a softmax is resulting in a prediction.